Hello TSAT viewers. Last class lo manam random variables topic start chesam. In this class we will continue the random variables topic. So MGF is nothing but the moment generating function. Let us consider there is a random variable x. For this, the moment generating function is given by, it is generated by mx of t, and it is given by expectation of e power tx. When you expand this, summation e power tx into p of x. Now when you expand this e power tx, become summation 1 plus t into x by 1 factorial plus t into x whole square by 2 factorial so on into p of x. Now into p of x so on. This will give us summation t power x by x factorial into mu x dash. So why I am writing mu x dash? Summation x into p of x, that is mu1 dash. In the second term, summation tx square by 2 factorial into p of x, summation x square into p of x, then I will get mu2 dash like this. Now this is the moment generating function, and when you differentiate this moment generating function with respect to t and substitute t is equal to 0, then we will get raw moments. Raw moments are nothing but non-central moments. That's why the name moment generating function for this CGF. CGF is given by expectation of e power itx, and it is generated by phi of x, where I is equal to root minus 1. A slight extension of this moment generating function. Now we will see the distribution functions. In this, first we will check out the discrete distribution functions, and then we will go to continuous distribution functions. Now there is a random experiment which results to only two outcomes. They are mutually exclusive events. It's a random variable. There is a random variable, and which results only two outcomes, that is success and failure, and this success with a probability p and this failure with a probability q. You know that p plus q must be equal to 1. Now this kind of random variable which gives only two outcomes, that is success or failure with the probability p and q respectively, is nothing but Bernoulli trial. Which is nothing but a Bernoulli trial. Now when you repeat this Bernoulli trial once, let us consider it is a random variable x. It is taking either success or failure with respect to the Bernoulli trial. Now this x considers either 0 or 1 with respect to success or failure. 0 results to failure and 1 results to success. And this probability mass function for this random variable x is given by p of x is equal to x, which is equal to p power x into 1 minus p whole power 1 by x, where x takes the values only 0, 1 or 0 otherwise. So this is nothing but the Bernoulli distribution. Now when you repeat this Bernoulli distribution n times, when you repeat the Bernoulli distribution n times, there is a random variable x which takes the number of successes, in the n trials. Now in these n trials, let us consider there are x success and n minus x failures, and when you are repeating this Bernoulli trial n times, you have to remember some points here. Our n must be finite value, and the each and every trial you are doing, they must be independent. Suppose you are doing first time and also repeating the second time. The first time and second time, those events must be independent of each other. And in every event the probability P must be constant. It may be any value, but it must be constant for each and every trial. And each and every trial should result to two outcomes, either success or failure. Each and every trial must show either it is a success or a failure. N must be in finite number, and each and every trial must be independent of each other, and the probability of success for each and every trial P must be constant, and each and every trial must be a success or a failure, and there is a random variable X which takes the number of a success value. Then this random variable will follow binomial distribution. Under these cases, our random variable X will follow binomial distribution, and its probability mass function is given by P of X is equal to X, which is equal to NCX into P power X into 1 minus P power N minus X, where X takes values 0, 1, 2, so on up to N, and 0 otherwise. Here N, P are parameters, and X is a random variable, you know that. Its mean, the mean of the binomial distribution is given by NP, and the variance is given by NPQ. When you take the summation P of X is equal to X, that is nothing but summation NCX into P power X into 1 minus P N minus X, it will be equal to 1. So the best example we can give for a Bernoulli trial or Bernoulli distribution and also binomial distribution is, so let us consider when you are tossing a coin. It will result to only either head or a tail. So when coin toss cheyagane heads ani cheppanu, so the result will be a head or a tail. Naku head vaste it is a success, tail vaste it is a failure. So that is a Bernoulli trial. Have only two outcomes, and each outcome has the equal chances for coming. That is called the Bernoulli trial. Now when you repeat that event n number of times, that is you are tossing a coin, suppose n number of times. You are tossing a coin for n number of times. So in that n number of times there will be X heads and N minus X tails. Now my random variable X will consider the number of success, that is number of heads. Now this is a perfect example for a binomial distribution. Let us consider there is a X which is following the binomial distribution. We represent, when X is following a binomial distribution, we represent like this: X following a binomial distribution with n number of trials, and P is a probability of success in each and every trial. It must be a constant, and Q is a probability of failure. And we know that P plus Q is equal to 1. Now let us consider the two random variables X, Y. X is following binomial with N1, P1 and Q1, and Y is also following binomial distribution with N2, P2 and Q2. Basically we represent only N1, P1, Q2, mostly we will reject that. I mean, we don't include that here. Let us consider X and Y are, let us consider the two random variables X, Y, which are following binomial distribution. X is following binomial distribution with N1, P1. Y is also following binomial distribution with N2, P2. Now X plus Y, when you add two random variables, now check out here, it won't follow binomial distribution. It won't follow binomial distribution unless there is one condition. See the condition. X follows binomial distribution with N1, P, and Y also following binomial distribution with N1, P. Then in this case, X plus Y will follow binomial distribution with N1 plus N2 number of trials and P as a probability of success. What is the difference in these two cases? In these two cases, in the first case, we are taking X1 is following binomial distribution with N1 number of trials and P1 success. I mean, P1 is the probability of success in random variable x case. In the same way, in the random variable y case, it is following binomial distribution with n2 number of trials and p2 as the probability of success. So in this case, x plus y will not follow binomial distribution. In the second case, x follows binomial distribution with n1 comma p. Y also following binomial distribution with n2 comma p. That is, in this case, in x and y random variables, the probability of success is constant. Then x and y will follow binomial distribution with n1 plus n2 number of trials and p as the probability of success. This binomial distribution is not only important for its wide range of applications, but it also important drawing the various distribution functions. We are seeing binomial distribution is with n number of trials and p as a probability of success and q as a probability of failure. Now, when I repeat this n to infinitely large, when I repeat the n infinitely large and p, now when you repeat the n to infinitely many number of times, and the probability of success in each and every case is very small, very small. Now, the product of this infinitely large number and the very small number n p will reach to a constant, say lambda. Now, in this case, when you take random variable x, under these conditions, this random variable x will follow Poisson distribution. Okay, and the probability mass function of this Poisson distribution function is given by p of x is equal to x, which is given by e power minus lambda into lambda power x by x factorial, where lambda is greater than 0 and 0 otherwise. And here x will take the values 0, 1, 2, so on up to infinitely large number. So when you take the summation here, summation of p of x is equal to x, which is equal to summation e power minus lambda into lambda power x by x factorial, x by x factorial which will be equal to 1 here. This Poisson distribution has a wide range of applications in a day-to-day life. So the best examples, the best situations in which we use Poisson distribution is to count the number of mistakes in a page, or a number of phone calls, or we can say that number of accidents in a road. So like this, in many cases we will use the Poisson distribution. Now this Poisson distribution has the mean lambda, and which will be equal to variance. Mean and variance here it is equal in a Poisson distribution, which is very, very important. Let us consider two random variables. X is following Poisson distribution with lambda 1 and y is also following Poisson distribution with lambda 2. Now x plus y, the combination of these two random variables x plus y will also follows Poisson distribution with lambda 1 plus lambda 2. Here in this case, the lambdas need not to be constant. మనకు బైనామియల్ ఏమవ్వాలి, the probability of success must be constant in both the random variables, but here it is not that case. Now when you extend this, random variables x1, x2, x3, so on up to xn, when you add all these random variables and each is having the parameter lambda 1, lambda 2, lambda 3, so on up to lambda n, summation lambda I is equal to 1 to n. So now this summation xi will follow Poisson distribution with parameter summation lambda I, continuous distribution. So in this continuous distribution we will discuss only about the normal distribution, which is very, very, very important. Now this normal distribution, the function f of x is given by, the probability function f of x is given by 1 by sigma under root of 2 pi into e power minus half into x minus mu by sigma whole square, where mu takes the values minus infinity to infinity and x takes the values minus infinity to infinity. This normal distribution also is a limiting case of the binomial distribution. How? Let's check here. There are n number of trials and the probability of success is p in the case of binomial distributions. Now, when this n is finitely large, that means n is very large. In the Poisson distribution it is infinitely large, but in the normal distribution it is finitely large. అంటే మనం మెజర్ చేయగలిగేంత large number n. And p, it neither small or large, అంటే మరీ ఎక్కువగా ఉండకూడదు, మరీ తక్కువగా ఉండకూడదు. So in those cases our binomial distribution will tend to normal distribution, and where the normal distribution function is given by f of x is equal to 1 by sigma under the 2 pi into e power minus half into x minus mu sigma whole square. Under these cases our binomial distribution will tend to a normal distribution. Now this normal distribution has the mean is equal to mu and variance is equal to sigma square. Now let's consider there is a random variable x which is following the normal distribution. We will represent like this, n with mu and sigma square. That is, x is a random variable which is following normal distribution with mean mu and the variance sigma square. Now we will transform this random variable x. Like see here, there is a new random variable z which is equal to x, the random variable which is following normal distribution, with mean mu, that is x minus mu divided by sigma. Z is a random variable which is equal to x minus mu by sigma. And now this z will follow normal distribution with mean 0 and variance 1. Okay. Now this is called standard normal distribution, and this z is called as standard normal variate. Now, so in this standard normal variate we have mu is equal to 0 and sigma square which is equal to 1. The variance is 1. Now this has a wide range of applications in statistical inference and theory of estimations. So we will see it further. Now we will see the properties of the normal distribution. So when you draw the normal distribution probabilities in a graph, it will be like this. Is perfectly inverted bell shape. This perfectly bell shaped curve. Okay. Now in this normal distribution we have a mean is equal to mode is equal to median. In a perfectly normal distribution we have mean is equal to mode is equal to median, and it is perfectly symmetrical about mean. Like ante each side enta area untundo at side kuda ante area untundi. It is perfectly symmetrical about the mean. Now the highest peak, the peak of the curve is achieved at mean. As we are saying, mean is equal to mode is equal to median. The highest peak is nothing but mode. The highest peak is occurring at x bar, that is mean. Mean is equal to median is equal to mode, and the skewness beta 1 which is 0, as it is perfectly symmetric, the skewness will be equal to 0, and the kurtosis is nothing but peakiness of the curve which is perfect, which is the value is equal to 3, beta 2 value is equal to 3. Let us consider x is a random variable which is following mu 1 comma sigma 1 square, and the random variable y is also following normal distribution with mu 2 comma sigma 2 square. Now this x plus y is also follows normal distribution with mu 1 plus mu 2 and sigma square, which is a combination of sigma 1 and sigma 2. There is x and y, both random variables are there which are following normal distribution, and the combination of this x and y will also follows the normal distribution. That is, a linear combination of any normal variates will also follow the normal distribution. Now very important property in the normal distribution is area property. So what is this area property? Now let us see, if you want to find out a probability with the intervals a to b. So we know that in a continuous random variables we find the probability with respect to the limits a to b or c to d, like that. So now if you want to find the probability from a to b, now it will be like integral a to b f of x dx. This is nothing but the area under the limits a to b. Now let us consider there is a value here A ఇక్కడ ఉందనుకోండి, B ఇక్కడ ఉందనుకోండి. Now the area between the A and B, so this will give us the probability of X lying between A and B. So that is very very important property in the normal distributions. Now in the area property only we see some important things here. Now if you want to find the probability within the limits A to B, we have seen just now how we do. Integral A to B f of x dx. Now if I want to find the probability which is lying between mu plus or minus sigma, mu plus or minus sigma, that is, look at here, x bar minus sigma and x bar plus sigma. So this is the area that is lying between mu minus sigma and mu plus sigma. So why we are like being very specific about this is, so the percentage of numbers, the percentage of data that is covered within the limits is almost 65%. The 68%. So the 68% of the data of the normal distribution will be lying in between x bar minus sigma and x bar plus sigma. Probability of x plus or minus 2 sigma. Now these are the limits, x minus 2 sigma and x plus 2 sigma, and the area under this x bar minus 2 sigma and x bar plus 2 sigma, the percentage of the values that are there under these limits is 95%. So 95% of the data values of the normal distribution will be lying between x bar minus 2 sigma and x bar plus 2 sigma. And one more thing we have, x bar probability of the values lying between x bar plus or minus 3 sigma. X bar minus 3 sigma idi, x bar plus 3 sigma idi. So the values that are lying in between x bar minus 3 sigma limits and x bar plus 3 sigma limits is 99%. That means 99% of the data values in the normal distribution will be lying in between x bar minus 3 sigma and x bar plus 3 sigma, and the remaining 1% will be lying outside the limits. So that is very very important properties in the normal distribution which you have to remember the values. So x bar plus or minus 1 sigma లో 68% ఆఫ్ డేటా ఉంటుంది, x బార్ ప్లస్ ఆర్ మైనస్ 2 సిగ్మా లిమిట్స్లో 95% ఆఫ్ ది డేటా ఉంటుంది, x బార్ ప్లస్ ఆర్ మైనస్ 3 సిగ్మా లిమిట్స్లో విల్ హ్యావ్ 99% ఆఫ్ ది డేటా. Now this we can also say in other words. We are seeing about the normal distribution x, we are transforming that to standard normal variate z, which is following normal distribution with 0, 1, and it has the probability mass function f of z is equal to 1 by under root over 2 pi into e power minus half z square. Now when you are taking the limits x bar minus 1 sigma and x bar plus 1 sigma, the z values will become minus 1 and plus 1. As we are saying, x bar we are making it to 0 and sigma it is 1. So 0 minus 1 into 1 it will become minus 1, 0 plus 1 into 1 it will become plus 1. The same way here z value will become minus 2, here z value will become plus 2, here z value will become minus 3, here z value will become minus 3. Okay, the area under z is equal to minus 3. Now probability of z lying between minus 1 and plus 1, which is equal to 0.68, that is 68%. The same way probability of z lying between minus 2 to plus 2, which is equal to 0.95, that is 95%. The probability of minus 3 to plus 3, which is equal to 0.99. Continuous distributions. So in these continuous distributions, we will see about normal distribution, which is very very important. Now we will see in the binomial distribution we have n number of trials which is repeating and the probability of success is p. Now here when n is finitely large, and p is neither small ఆల్ లార్జ్, మరీ పెద్దగా ఉండకూడదు, మరీ చిన్నగా ఉండకూడదు. సో అండర్ దీస్ కండిషన్స్ అవర్ బైనామియల్ డిస్ట్రిబ్యూషన్ విల్ టెండ్ టు normal distribution, and the normal distribution function is given by f of x is equal to 1 by sigma under root of 2 pi into e power minus half x minus mu by sigma whole square, where x will take values minus infinity to plus infinity and mu values will take minus infinity to plus infinity. Now it has mean is equal to mu, variance is equal to sigma square. Now let us consider x is following this normal distribution. We will represent like this when x is following normal distributions with mu and sigma square. Now this is a random variable x. Now I will transform that random variable x to z. My transformation function will be z is equal to x minus mu by sigma. Now this z is a new random variable that is transformed from x. Z is equal to x minus mu by sigma. Now this z will follow again a normal distribution with mean 0 and the variance 1, and its function is given by f of z is equal to 1 by 2 pi into e power minus half z square, minus half z square. Now this function is called standard normal distribution function, and this variate z is nothing but standard normal variate. Now we will see the properties of this normal distribution. We have mean is equal to median is equal to mode in the normal distribution. Now see the graph here. When you plot the normal distribution function in the graph, it is perfectly symmetrical. It is perfectly symmetrical and inverted bell shape, and it is symmetrical about x is equal to, it is symmetrical about the mean, that is x bar. Same here, it is the line of mean is equal to median, which is also equal to mode. X comma y, which are following normal distribution, the linear combination of this x plus y is also the same normal distribution. So the very important property in the normal distribution is the area property. The area property. Now I have to find the probability of x within the limits a to b. We will calculate it as integral a to b f of x dx. So this is nothing but the area under the limits a to b in the function f of x. This will be like this. Let us consider there is a value a and there is a value b. The area under these limits a to b will give us this value integral a to b f of x dx, and that is the probability lying within the limits a to b. Now the important area properties we will see is probability of mu minus sigma less than or equal to x less than or equal to mu plus sigma, and the same thing we can write it as probability of minus 1 less than or equal to z less than or equal to 1 in terms of z, and it will be equal to 0.68. Same way, probability of mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma, which we can also write as probability of minus 2 less than or equal to z less than or equal to 2, which will be equal to 0.95. Probability of mu minus 3 sigma less than or equal to x less than or equal to mu plus 3 sigma, which is equal to probability of minus 3 less than or equal to z less than or equal to 3, which is equal to 0.99. So what are these values representing? When you draw a limits from x bar minus 1 sigma to x bar plus sigma, the area lying under these limits, is 68%. That is the data of the normal distribution lying within the limits x bar minus 1 sigma to x bar plus 1 sigma is 68% of the data. Now when you take the limits, second limits x bar minus 2 sigma and x bar plus 2 sigma. So the values that are lying in between x bar minus 2 sigma and x bar plus 2 sigma is 95, that is 95% of the values are lying in between x bar minus 2 sigma and x bar plus 2 sigma. Now consider the third value, x bar minus 3 sigma and x bar plus 3 sigma. So when you consider the probability is 0.99, that means the values, okay, it is 99%. So that is in the normal distribution, 99% of the data will be lying in between x bar minus 3 sigma and x bar plus 3 sigma, and the remaining 1% will be lying in the tails out of the limits x bar minus 3 sigma and x bar plus 3 sigma. So these are very important values which you have to remember, which will use these values in the theory of estimation and statistical inference topics. Now see here. So we can also write x bar minus 1 sigma and x bar 1 plus 1 sigma as z is equal to minus 1 and z is equal to 1, and x bar minus 2 sigma as z is equal to minus 2 and z is equal to plus 2, and here we write as z is equal to minus 3 and z is equal to plus 3. This is in terms of standard normal variates. See the example questions here. So in the normal distribution, the probability has the maximum value at. So we have already seen in the graph, the maximum probability will be occurring at the mean. Look at the second question. Sum of independent finite number of Bernoulli random variables with constant p gives the distribution. So we have seen how the binomial distribution is formed. That is, when you repeat the Bernoulli distributions with n number of times with a constant probability of success p, then you will get the binomial distribution. Look at the third question. Mean is equal to variance in the dash distribution. So we have seen the Poisson distribution properties where the mean is equal to variance is equal to lambda. So like this, the concept questions can be asked in the examinations. In the next class, we will start the correlation unit. Thank you.